Welcome back to the Aptos blockchain series. And today we have an architecture session. We are exploring the integrated design that makes Aptos stand out in the blockchain space. The Aptos team set out with ambitious goals to create a blockchain capable of processing hundreds of thousands of transactions per second while still maintaining robust security, seamless upgradability, and an improved experience for both users and developers. Let's break down the key components of the Aptos blockchain. At its core, we have the consensus layer, which utilizes the DMBFT protocol, the execution layer featuring a parallel execution engine. This is where Aptos truly shines. Supporting these, we have the storage layer, which employs a versioned database system, and the network layer handling peer-to-peer communications. These components work in tandem to deliver a blockchain that's fast, secure, and highly scalable. Now let's look into the consensus mechanism, which is DMBFT. This Byzantine fault tolerance protocol is crucial for maintaining network agreement even in the presence of malicious or faulty nodes. DMBFT offers several key advantages: high throughput, processing thousands of transactions per second, low latency with confirmations in mere seconds, and deterministic finality, eliminating the need for multiple confirmations. DMBFT operates as a leader-based protocol where one node proposes a block and others vote on it. To prevent centralization, the leader role rotates regularly. The protocol also employs pipeline voting, allowing the network to process multiple blocks simultaneously, further enhancing throughput. Compared to proof-of-work systems like Bitcoin, DMBFT is significantly more energy efficient and faster. It also outperforms proof-of-stake systems in terms of finality time. What sets DMBFT apart is its optimization for blockchain use, particularly its synergy with Aptos' parallel execution engine. This combination of DMBFT and parallel execution is what enables Aptos to achieve its remarkable speed and efficiency. By allowing for the simultaneous processing of numerous transactions while maintaining a secure and decentralized network, Aptos is pushing the boundaries of blockchain technology. Now let's move on to what truly sets Aptos apart: its execution model based on parallel execution. At the heart of this model is block STM, or software transactional memory. This innovative approach allows Aptos to process multiple transactions simultaneously, dramatically increasing throughput. Imagine a traditional blockchain as a single-lane highway, where transactions move one after the other. Aptos with block STM is more like a multi-lane expressway. It groups transactions into blocks and attempts to execute all transactions within a block concurrently. This optimistic execution assumes transactions will not conflict, but has built-in mechanisms to detect and resolve conflicts when they do occur. The efficiency of block STM lies in its conflict resolution. In most cases, transactions don't interfere with each other, allowing for massive parallelization. When conflicts do arise, block STM resolves them swiftly, minimizing slowdowns. This approach enables Aptos to potentially process hundreds of thousands of transactions per second, which is a significant leap over traditional sequential models. The advantage of this parallel execution model are clear when compared to sequential systems. While sequential models hit a ceiling in transaction processing speeds, Aptos' parallel execution can fully utilize multi-core processors, scaling efficiently with more powerful hardware. It's also more resilient. A slow transaction won't hold up the entire process. Now let's turn our attention to how Aptos manages all this data. The storage and state management in Aptos are designed to be as efficient and scalable as its execution model. Aptos employs a versioned database system. Every time the blockchain state changes, a new version is created. This approach offers several benefits. It allows for easy historical queries, simplifies operations like state reversions, and helps maintain consistency across the network. State versioning is a key feature where each account and piece of data has its own version number that increments with modifications. This granular versioning makes tracking changes and ensuring network-wide consistency straightforward. To prevent the database from ballooning in size, Aptos implements state pruning. This process safely discards old state data that's no longer needed, while still maintaining the ability to prove the correctness of the current state. It's a crucial feature for long-term scalability. One of the most innovative aspects of Aptos storage system is its use of a Merkle accumulator for efficient state proofs. This data structure and evolution of the Merkle tree allows for rapid generation of proofs of the current state, even as the dataset grows. This is particularly important for light clients that need to verify data without downloading the entire blockchain. The combination of these storage and state management techniques results in a system that's not only fast and efficient, but also maintains a complete and verifiable history of the blockchain state. This approach supports Aptos' high transaction throughput while ensuring strong security guarantees and enabling complex features like rollbacks and historical queries. Now let's see how Aptos manages its network of nodes and facilitates peer-to-peer communication. The network layer is crucial for maintaining the decentralized nature of the blockchain while ensuring efficient data transmission. Aptos utilizes a sophisticated peer-to-peer networking protocol built on libp2p, which is a popular modular network stack in the blockchain world. This protocol handles everything from establishing connections to routing messages between nodes. Its modular design allows for flexibility and future upgrades, ensuring that Aptos can evolve its networking capabilities as needed. Peer discovery and management are key components of the Aptos network. When a new node joins the network, it needs to find other nodes to connect to. Aptos employs a multi-pronged approach for this. It uses seed nodes, which are well-known nodes that new participants can initially connect to. Additionally, it leverages a distributed hash table or a DHT for decentralized peer discovery. Once connected, nodes continuously evaluate their peers, monitoring factors like response time and reliability. This ongoing assessment allows the network to self-heal by disconnecting from underperforming or suspicious nodes. This creates a robust, attack-resistant network that can maintain integrity even in the face of network partitions. Data synchronization is another critical aspect of the network layer. When a node joins the network or comes back online after being offline, it needs to catch up with the current state of the blockchain. Aptos uses a process called state synchronization, allowing nodes to quickly download the latest state without processing all historical transactions. This is where the version storage system we discussed earlier proves its worth. For ongoing synchronization, Aptos employs a gossip protocol. When a node receives new transactions or blocks, it sends this information to its peers, enabling rapid dissemination of new data across the network. This approach ensures that all nodes can stay up to date efficiently. Now let's discuss how Aptos handles governance and upgrades, a crucial aspect for any blockchain aiming to remain relevant and adaptable over time. Aptos implements an on-chain governance mechanism, meaning that decisions about protocol changes or upgrades are made through a voting process that occurs directly on the blockchain. Here's how it works. Anyone can submit a proposal for an upgrade or change on the Aptos protocol. These proposals are submitted as special transactions on the blockchain, ensuring transparency and traceability. Token holders can then vote on these proposals, with voting power typically proportional to the number of tokens held. This system ensures that those with the most stake in the network have the most say in its future. If a proposal passes, it can be automatically implemented. This is where Aptos' upgradability feature comes into play, allowing the blockchain to evolve without requiring disruptive hard forks. The entire process happens on-chain, making it fully transparent and auditable. Anyone can see what proposals are up for vote, how the voting is progressing, and what changes have been implemented. This governance model strikes a balance between stability and innovation. It allows Aptos to adapt and improve over time while maintaining decentralization. No single entity can force through changes without community consensus, ensuring that the evolution of the protocol aligns with the interests of its users and stakeholders. So now for the conclusion summary of this video. DMBFT consensus provides fast, secure consensus with deterministic finality. And then we have parallel execution with block STM, which enables unprecedented transaction throughput. And then we have efficient storage with version databases and Merkle accumulators, which help with balancing performance with data integrity, and a robust networking layer, which ensures reliable peer-to-peer communication and rapid data synchronization. And then we have on-chain governance, which allows the protocol to evolve in a decentralized manner. All right, thank you so much for watching, and I'll see you in the next video.